All right, let's go ahead and get started. So I'm going to be jumping back and forth between the Pear Deck screen and my Zoom screen. And I'm going to need you guys to go back and forth between those two screens as well, because that's how I'm going to write on the screen, assuming I can find my marker. There we go. So let's just start off on the Zoom screen. Some of you, I recognize your names, were here last week, and we spent a lot of time looking at free body diagrams. So we're going to quickly review those. So I would like you guys to draw on your screen, the Pear Deck screen, and try to draw a free body diagram for problem number 1 that you see now. For those of you that just came in, make sure that you go ahead and join our Pear Deck presentation by going to joinpd.com and entering the code NYYASX. Again, that's joinpd.com, code NYYASX. And when you do, I want you to go to that Pear Deck screen and try to draw a free body diagram for problem 1. All right, I'm going to see what you guys are thinking. All right, those look pretty good. One thing that we need to do is we need to make sure we label the forces, not just use arrows. And I see a couple of problems with the normal forces. So let's flip back over to my screen now, the Zoom screen. And I want to be able to write on the screen for you guys. So let me get this pulled up. All right, so here's what we want to do. So let's take our incline. That's a terrible incline. Let me try that again. All right, so let's say we have some kind of box up here on our incline. And it's sliding down the plane. There's some kinetic friction acting on it. Draw a free body diagram that depicts all the forces. All right, so normally the first thing that you would want to draw in when you go to a free body diagram for a box on an incline is the weight. So we're going to label that as FG, or the weight. Now, when you're working free body diagrams, you have to break that weight into 2 components. One component that's perpendicular to the plane, and one component that's parallel to the plane. And I'm going to label those F parallel and F perpendicular. Now, those are not part of your free body diagram. I'm going to take those off in a minute, but I wanted to just put them here for just a second. This force, the parallel component of the weight, is the force that pushes the box or pulls the box down the plane. This component is equal and opposite to the normal force that acts between the box and the surface, the plane itself. So those are both going to be important when we start calculating things. Let's take those off for a minute, though. So the other force that we have here is we do have a normal force. And remember that normal means perpendicular. The normal force is always perpendicular to the surface. So we need a force that's at a 90-degree angle between the box and the surface, something like that. And that's our F normal. And then the other force that some of you did show was the force of kinetic friction, the frictional force. And we know that always acts opposite of motion, friction does. So if the box is going down the plane, the frictional force needs to be acting up the plane. And I'm going to call mine FF. for frictional force. That's the typical terminology. All right, any questions there on our free body diagram for number 1? All right, let's go back then to the Pear Deck screen. All right, so here's problem 2. I want you guys to go ahead and take this and try to work out problem 2. And go ahead and type in your answer, A, B, C, or D on problem 2. Some of you probably just know this answer because you've worked this kind of problem a bunch of times. Some of you will have to work it out. All right, I got 2 responses. Let's keep going here for a minute. Let's take a look at what you guys who have put in an answer are thinking so far. So half and half B and half C. All right, so let's go back now to my PowerPoint screen, your Zoom screen. And let's think about this for a second. So here's that incline. Here's our box. All right, and we know that box is on the incline, so we're going to draw in the weight. That's FG. Our angle of our incline is theta. All right, like I told you before, when we're working these incline plane problems, we need to break that weight into 2 components. One perpendicular to the incline plane itself, and one parallel to the incline plane itself. When you do that, this angle right here is always going to be the same as your angle of incline. So this angle right here is theta. So we know that this side of our triangle is our weight. That's mg. It's our weight, mass times gravity, weight. So we can use that side, since it's going to be the hypotenuse of a triangle, we can use that and some trig functions to solve for the parallel and the perpendicular component. Since the parallel component is opposite of this angle theta right here, I can use sine to find it. So I'm going to say the sine of theta is equal to the opposite side, which would be F parallel, over my hypotenuse, which would be the weight, mg. Well, that means that F parallel equals mg times sine theta, if I just solve that for theta. Now, we could also find the perpendicular component here. It's not going to be necessary for this problem, but if we wanted to find the perpendicular component, we could use cosine. And cosine of theta is equal to the adjacent side, which would be my perpendicular component, over my hypotenuse, bmg. So my perpendicular component is mg times cosine theta. Now, here's what's important, though. We're looking for the acceleration down the inclined plane. It tells us there's no friction. Since there's no friction, the only force acting along the inclined plane is this force right here. It's the only force, therefore it's the net force. Since it's the only force acting along the plane, it is the net force acting along the plane, which means we can set that force equal to net force, which is MA. So essentially what we're doing is we're taking our mg sine theta force. And since it's the net force, we're setting it equal to what net force is equal to, which is mass times acceleration, Newton's second law. So in this case, the masses cancel out, and acceleration equals g sine theta, which was answer C. Does that make sense? Anyone have questions on that one? All right, let's go back to the Pear Deck screen then, and let's try one more similar problem. So you guys, this is similar. Go ahead and take a stab at number 3. Going to work very similarly to 2 with just one added wrinkle. So again, take a stab at number 3. All right, I got 2 answers. You guys, the rest of you, go ahead and at least take a stab at it. All right, I'm going to see what you guys are thinking. So I'm seeing a lot of A's. Looks like everybody's choosing A. So let's go back to PowerPoint here for a minute. Bear with me for just a second. This menu is not cooperating. There we go. So again, back to our inclined plane. Drawing our weight. That's FG, or M, let's just use it as MG. It's the weight. Drawing our components of that weight. One perpendicular, one parallel. We saw in the last problem that the parallel component was equal to mg sine theta. And we saw that the perpendicular component was equal to mg cosine theta. Now remember that we said that this perpendicular component is equal but opposite to the normal force. So this is also the force of normal, or the normal force. Now, in this case, in this problem, there's friction. So we know that this parallel component is pushing the box down the plane, but the frictional force is acting up the plane, which means the net force would be equal to the parallel component acting down the plane minus the friction force acting up the plane. We're using that as the negative direction. That's what that negative means. It's acting in the opposite direction as the parallel force. So if we put some symbols on this, our net force is MA, and that's equal to F parallel, which is mg sine theta, minus our frictional force. And our frictional force, you guys, I hope know the frictional force is mu times N. That's the formula for frictional force, mu times N. Now, in this case, N is the normal force. And we saw up here that this is the normal force, mg cosine theta. So if we make a substitution there for N, and we substitute in mg cosine theta, we can see that the masses cancel, because the mass is part of every term. So we end up with an answer here. Whoops. That's equivalent to choice A, g sine theta minus mu times g cosine theta. All right, questions on problem 3. So a lot of inclines so far. Today is going to be mostly inclines and friction. We're going to keep coming back to those two topics in almost all the problems that we work. That being said, let's get back to the PowerPoint, the Pear Deck rather. And let's look at problem 4. Now this one, if you understand how friction works, this one should be very quick. So go ahead and type in what you think the answer is to problem number 4. Don't overcomplicate this one. This one's as easy as it seems. All right, I'm gonna see what you guys are thinking. So D looks like what everybody's thinking. Let's go back to the PowerPoint. All right, the key word in this problem, or the key 2 words, those 2 words. This box is moving at a constant velocity. Because it's moving at a constant velocity, that means the acceleration is 0, which also means the net force acting on this object is 0. So if we have this box and we're pulling it one way with a force of 65 newtons, well, I hope that tells you that there has to be another force acting the opposite direction, 65 newtons, because the net force has to add up to be 0. 65 positive plus 65 negative. So the answer here should be 65 newtons to the left. And again, you know that because the box is moving at a constant velocity, which means there's no acceleration and therefore no net force. Does that make sense? Anybody have questions on problem 4? All right, well, back to Pear Deck then. Here's problem 5. Same problem, different question about the problem. So see what you can do with by finding the coefficient of friction. Going to see what you guys are thinking. So I'm seeing some A's. All right, let's get back to the PowerPoint. Take a look there. So remember that our equation for friction, I like to call it the fun equation. It's mu times n, where mu is the coefficient of friction, which is essentially a measure of how 2 surfaces interact with each other. And then n is the normal force. How much does the surface typically push up on the object setting on it? So when we're on a flat ground, which we're assuming the table's flat, the normal force is just going to be equal and opposite to the weight. So this is going to be 96 newtons. If we solve this equation for mu is going to be F, the frictional force, over the normal force. We found in the last problem that the frictional force was 65 newtons. And since we're on a flat table, that means the normal force is equal but opposite to the weight of 96 newtons. So we divide that out, 65 divided by 95, by 96 rather, and we end up with 0.667. So answer A looks good. In most cases, the coefficient of friction is going to be less than 1. There are some cases when that's not true, but if you've got to take a guess on an AP exam, guess the coefficients that are less than 1 if you're just blind guessing, because typically coefficient is going to be less than 1. Any questions on problem 5? Guys, be sure to ask if you have a question. I promise you I'll do my best to answer it for you. All right, so let's look at 6. Again, same question, mostly the same question. This time we threw another wrinkle at it. So this one's going to be just a little bit more complicated. See what you can do with it. All right, I'm going to give you about another minute on this one. All right, let's see what you guys are thinking. So D looks popular. Let's go back to the PowerPoint. So here's the trick. So here's our box. We know there's an applied force of 65 newtons going one way. There's friction acting the other way. But this thing's accelerating, and that tells you there's a net force. So in this case, the net force is going to be equal to the force of the applied force going to the right minus the frictional force going to the left. Well, we don't know. We don't know what the frictional force is, but we do know what the applied force is. We know this is 65. We can find the net force because we know the weight of the box. So we know that weight equals mg. So if we just divide 96 by g, 10 meters per second square, we end up with a mass of 9.6 kilograms. Therefore, the net force is equal to 9.6 mass times the acceleration of 3. That's 28.8. And that's over here to the right. So if we do a little rearranging of our equation up here, we could see that and I'm just going to solve this equation out for frictional force up top. So frictional force would be equal to FA minus F net. And all I did is just solve this equation right here for frictional force. My applied force was 65 newtons minus my frictional force, 28.8 newtons. We end up with 36.2. Now, it looks like when I worked this problem originally that I probably used 9.8 for a G instead of 10. So this is the answer we're looking for right here. That's what it's going to come out to be if you actually use 9.8 instead of 10. So 36.2 if you use 10, 35.6 if you use 9.8. All right, questions on that one? All right, let's get back to our Pear Deck screen. And let's try problem 7. All right, so take a minute and try that one. Let's take about another minute to finish this one up. All right, so we've got an even split here between A and B. So let's go back to our PowerPoint and let's see what's going on here. So we're applying a force of F at an angle of 60 degrees above the horizontal and to the left on a box of mass M. So here's our box, mass M. So let's think of it as if we have like a rope attached to it. And we're pulling up on this rope. And let's just kind of extend the ground upward. This angle, 60 degrees. So the angle between the rope and the ground is 60 degrees. No friction acts on the system. What is the value of the horizontal acceleration of the system? Horizontal acceleration, which means we need to know what's the horizontal component of this force F, because we're pulling on this thing like so. We need to know just a horizontal part of that. So we're going to draw down a vertical, and we're going to break this force of F into components. What we're going to call the parallel component, or I'm just going to call it I'm going to call it F to the left, and I'm going to call this F to the up, like so. The force that we're worried about, though, is this force, the horizontal component. So let's use some trig. This is the adjacent side to our 60-degree angle. So to find it, we would use cosine. And we would say cosine of 60 equals our adjacent side, f to the left, over our hypotenuse, which is that big F, which means if we solve that for f to the left, f to the left equals f cosine 60. So that's our net horizontal force. We're looking for what's the acceleration. That's our net force. We know that F net equals ma, which means that A equals F net over m. So plugging in our values, our net force is F cosine 60 over m. Now, that's going to mean that some of you probably picked C. And in this case, C is not the best answer. And the reason C is not the best answer because of that one word right there, to the left. Remember that we typically call left negative. So the best answer, A, negative F cosine 60 over m. All right, does that make sense? Are there questions on that one? All right, let's get back to Pear Deck then. Go to number 8. All right, they like to give problems with blocks and ropes and tension. So this is a good example of that type of problem. See what you can do with this problem. Take a look at what you guys are thinking. So C and D. So let's go back to the PowerPoint. All right, so here's what we know. We know that we're pulling on this rope over here, pulling it this way with a force of F. There's no friction. That means that this F is the net force acting on this whole system, the whole thing. So the net force is equal to F, and we know that net force equals ma. Well, in this case, we're talking about the net force acting on the system. This F is acting on the whole system, which means the system force, the system net force is equal to the mass of the system, 5 kilograms, times the acceleration of the system. So if we solve that for acceleration, the acceleration of our system is equal to F over 5 kilograms, or just think of it as F over 5 for right now. Now that's the acceleration of the system, but since these two blocks are connected by a rope, they're both going to accelerate at this rate, F over 5. We're trying to find the tension in this rope. Well, the tension in this rope is just the net force that acts on this box, box A. So if we think about F equals ma just for box A, well, the net force acting on box A is that tension. And that tension, again, is equal to the net force, and that's equal to M. This time we're talking about just box A. So the mass of box A is 2 times the acceleration of box A, which is F over 5. So we took the mass of box A times the acceleration of box A to get the net force acting on box A, which is that tension. And notice that that is answer C, 2 times F over 5. So if you're struggling with problem 8, that's a kind of problem that you need to make sure that you master, because you're going to see those kinds of problems on the AP exam. Boxes and strings and tensions, they're going to be there every time. Questions on 8 for me? All right, let's get back to Pear Deck then, see what we got coming up on problem number 9. All right, so back to inclines this time. So see what you can do with this one. I got a question in the chat about on that last problem, why does the system acceleration equals F over 5? So I just took Newton's second law and I solved it for acceleration. A equals F net over M. So the net force acting on that system, since there wasn't any friction, was just F. And the mass of that whole system was the 3 kilogram box plus the 2 kilogram box, 5 total kilograms. So the net force acting on the system along that incline, along the flat surface at least, was F, divided by the mass of the system, which was 5. So therefore the acceleration of the system was F over 5. Let me know if that doesn't make sense. Looks like it did. Awesome. And I will tell you, it looks like on problem 9 that I used 9.8 again as G. So you may have a little bit different rounding number when you work this one out. You may not get one of these answers exactly, but pick the one that's closest to what you come up with. Remember, on the AP exam, you're always going to use 10 meters per second squared for G. I'm in the habit of, I've been teaching physics so long of using 9.8, and I'm trying to break that habit. All right, so some of you are thinking B. Let's go to the PowerPoint now and let's see what's going on with that. Oops, got ahead of myself there. So here's our incline. It's a 45-degree angle. So we have this box that's accelerating at 1 meter per second squared down the plane. What net force acts down the plane? Well, since the acceleration is along the plane, we know that F net equals ma. We know that's A. And since the weight of the box is 450 newtons and weight equals mg, mass therefore equals weight divided by g. So if we take 450, the weight, divided by g, 10, we get a mass of 45 kilograms. So 45 kilograms, the mass, times the acceleration, should give us 45 newtons. So this should be 45.0 if we use 10 meters per second square. So B is what we were looking for. Does that make sense? Any questions on that one? All right, back to Pear Deck then. Problem 10 is going to be about that same prompt, just it's going to ask you something different about the prompt. Here you go. All right, I want to see what you guys are thinking. Again, this may have a slight rounding issue. I may have used 9.8 again on this one. You guys are thinking D. So let's go back to PowerPoint and let's see. So we want to know what frictional force acts on the plane. So we got to draw in our incline. Again, it's 45 degrees. Draw our box. Drawing the weight of that box. We know that's 450 newtons. We're going to break that weight into two components, one perpendicular, one parallel. Remembering that if this angle down here is 45, that angle right there is also 45 degrees. Here's F parallel. Here's F perpendicular. So let's solve for F parallel to begin with. So I'm going to use sine to find F parallel. Sine 45 equals F parallel over the hypotenuse, which is the weight, 450. That means F parallel equals sine 45 times 450. So I'm going to go ahead and do the math on that. So the sine of 45 times 450. That comes out to be 318.2. Turns out for right now, we don't need the perpendicular component. We'll need it in a minute. Let's go ahead and find it while we're here. So the perpendicular component is the adjacent side to our angle. So we'll use cosine to find it. So it's going to be F perpendicular over the weight. And we're going to get the same value because the cosine and sine of 45 are the same. So F perpendicular equals 318.2 newtons. Important thing here, though, is that we have, let me make a little space so I have more room to write here. Whoops. Not sure what I did there. Let's go back here. So here's what we've got acting along the incline. We have that parallel force, F parallel, pushing the box down the plane, 318.2. We know there's a frictional force acting up the plane. We don't know how much that is. But we also know there's a net force. And we figured out in the problem a minute ago that the net force was 45 newtons down the plane. So let's write out an equation for that. So our net force down the plane would be equal to our parallel force minus our frictional force. Because the parallel force is pushing down the plane. The frictional force in this case is pushing up the plane. That means if we solve this equation for frictional force, F of friction would be equal to F parallel minus F net. I just took that equation, solved it for the frictional force. So we know that our parallel force was 318.2 newtons. We know that our net force is 45 newtons. So we do the math on that, 318.2 minus 45. We end up with 273.2. And again, I think I used 9.8 when I worked this problem out. So that's our closest answer, answer B. But if you use 10, your answer is going to be more around 273 instead of around 272. All right, does that make sense? Any questions on 10? All right, well, let's get back to a PowerPoint. Then we've got, I think, one other problem related to this prompt. Back to Pear Deck. And we want to know what normal force acts on this box. All right, remember, and this is a key thing, and I want somebody to unmute and answer me here. We said in these inclined plane problems, how do you find the normal force? Somebody unmute and tell me, how do you find the normal force in these inclined plane problems?
You said it was equal to the perpendicular force of gravity.
Yeah, so you take your weight and you find the perpendicular component of the weight, which we already did when we were working 10. Somebody remind me what the perpendicular component of our weight was in problem 10. Anybody remember?
318.
318. So that's equal and opposite to the perpendicular component of the weight. So our answer on problem 11 is 318. So you guys just go ahead and mark that one so that you have your answer in Pear Deck. And we'll go ahead and go to the next question. And there is one more question related to this prompt. And then after this, we'll skip ahead and we'll work in FRQ and then we'll call it a day. So go ahead and see what you can do on this one. And I'm going to help you guys out for a minute. I'm going to go back to my PowerPoint for just 1 second because you've got to remember some numbers from the previous problem to be able to work this one. So let's backtrack for a second. So remember that we said the frictional force, the value of the frictional force was about 273 newtons. And also remember that our normal force was about 318 newtons. So you've got to know those two numbers to work this problem. Frictional force, 273, let's use 273, and the normal force, 318. If you know those two numbers, this shouldn't be too bad of a problem to work. So looking like A, let's go to the PowerPoint real quick and take a quick look at this one. So what you got to remember on this is, that's the normal force. You got to remember this friction equation. We're solving for the coefficient of friction, mu. So mu is equal to the frictional force divided by the normal force. We found in previous problems that the frictional force was 273 newtons. We also found that the normal force was 318 newtons. Notice that the newtons cancel out. So this coefficient of friction is like a ratio. It's not going to have any units at all. If we divide 273 by 318, we end up with about 0.855, 858, depending on how you rounded it. So A looks like our best choice here. Any questions on that one? All right, I want us to skip to an FRQ here at the end. So let's get back to our Pear Deck. Again, I'm skipping a couple of problems. Here's the one I want us to look at. So I want you guys, so you can draw on your screen now. So I want you to read the prompt and look at the diagram up at the top. And I want you to draw in the free body diagram on part A. So go ahead and draw that on your screen. Use those dots under part A and literally draw the arrows to represent the free body diagram on that one. Let's see what you guys are thinking. Remember, when you're doing these free body diagrams, you need to label the forces. So don't just draw the arrows. Make sure that you label them. So here's, I'm going to go to the PowerPoint for a minute. So jump over to the PowerPoint with me for a second. So on block 2, the force pushing down on block 2 is the weight of block 2. So I'm going to label that as FG. And then the force acting up on block 2 is the tension in that rope. Well, we know that the tension in the rope is less than the weight of block 2 because block 2 is bigger than block 1, which means when you let this go, block 2 is going to go down. It's going to accelerate down, and block 1 is going to accelerate up. So that means that this force has to be greater than this tension force. So that's the main thing, that you show that FG is longer than T. It's bigger than T. Over on block 1, we got the weight of block 1 acting down, but we know this block's going to accelerate up because block 2 is bigger, which means the tension acting on that one has to be bigger. Has to be bigger than the weight of block 1. But that tension should be the same as this tension. So these two need to be the same length, whereas the weight of block 1 should be smaller. Maybe something like that. So two things are going to be looking for. Is the weight of block 2, is that arrow longer than the weight of block 1? It's got to be because it's bigger. And are the tensions the same in both cases? That's really what they're looking for you to get the point on that one. Let's go ahead, while we're on this slide, let's go ahead and look at part B. Derive the magnitude of the acceleration of block B. Express your answer in terms of M1, M2, and G. All right, they're always going to be asking you this kind of problem on the FRQ. And what you've got to think about first is, well, what's the net force? And I'm hoping that you see that the net force acting in this system is really the difference between the weights of these two blocks. So the net force is going to be equal to the mass of 2 times G, the weight of that block 2, minus the mass of 1 times G. That's the net force acting on this system. Well, we're looking for the acceleration of the system. Well, we know good old F net equals MA. Again, we think about the whole system. So that means my system acceleration is equal to the net force of my acting on my system divided by the mass of my system. So in this case, the acceleration is going to be the system net force, which is this, m2g minus m1g, over the mass of the system, which is the mass of 1 plus the mass of 2. That's what we're looking for on that. So you got a point for putting the answer, but you also got a point for showing all these steps. So make sure, show this, then show this, and then show this. You can get points for showing your work and getting the right answer. Just writing down the right answer might get you a point, but it won't get you the 2 or 3 points that part B is worth. If it says derive, they want to see your work. So show this, then show this, then show this. Does that make sense? All right, there's one more part to this problem. Here it is. So now we added block 3 up here sitting on the table. Everything else is the same. There's no friction between block 3 and the table. So indicate whether the magnitude of the acceleration of block 2 is now larger, smaller, or the same, and explain how you arrived at your answer. So somebody unmute and tell me what you think. Is the acceleration of block 2 now larger, smaller, or the same? Someone unmute and tell me what you think. Anybody. I hate to have to call on somebody. Somebody unmute and tell me what you think.
Would it be the same because there's no friction between the table and block 3?
Okay. So remember, the net force a minute ago was the difference between the weight of block 2 and the weight of block 1. Has that changed? Has the net force acting on the system changed?
No.
No, because the weight of this thing is getting canceled out by what? What's canceling out the weight of block 3? Help me out, guys. What's canceling out the weight of block 3? The weight of block 3 pushes down. What's pushing up? Canceling it out. Looks like somebody put an answer in the chat here. Let's see what we got. So we got the normal force, which is exactly right. So block 3 doesn't affect the net force acting on the system, but it does affect what part of the system? Doesn't affect the net force, but it does affect what part of the system? And there we go, the mass. So here's the thing. Remember that acceleration of the system is equal to the net force of the system divided by the mass of the system. Well, we just got through saying that this part doesn't change, but the mass of the system went up when we added block 3. So if we're now dividing the same net force by a bigger mass, what happens to our acceleration? So we got another chat answer. Let's see what we got here. So it decreases. Exactly. So our answer here, smaller. And the reason it's smaller is because since the net force acting on the system didn't change, but the mass increased, the acceleration of the system is therefore less, smaller. All right, so that's A, or that's C. Any questions on that one for me? All right, well, I appreciate you guys being here today. I hope it helped. I'm gonna end this session in just a second, and when I do, you should get your Pear Deck takeaway. And remember, that'll show up in your Google Drive account, and it'll be under Shared with Me in your Google Drive account. We will not have this weekly session next week because we have our normal A+ College Ready study sessions next week. So the next one of these will be 2 weeks from today. Still be on Wednesday at 4 o'clock, but it'll be 2 weeks from today. All right. Hope to see you guys then. Thanks again for being here. I appreciate it.